Hello, everybody. Mr. Hinnon here, and this time we're going to take a look at series and parallel circuits. We're trying to look at what happens if I take different objects and I connect them together in certain patterns in our electrical circuits. We had a little bit of this in Physics 1, so this is kind of hopefully a continuation of that. So the first kind is what we call series circuit, and the main idea with a series circuit is that they're connected in such a way that the same electrical current is passing through it. In other words, there's only one path for the electricity. So looking at my picture here, if I use conventional current, which is current coming away from the positive charge here, then it's going to flow up and then go through this resistor, pass through it, and then come through this resistor, and then eventually come back to the battery. So these two resistors are connected in what we call series. Because of that, the total voltage, this voltage of the battery, is going to be split between these two. So resistor number 1 is going to get a certain amount, and resistor number 2 is going to get a certain amount. So then if I replace that with Ohm's law, that V equals IR, we should be able to come up with that IR1 equal plus IR2 is going to equal my voltage. Since the current is the same, I can factor that out, and then eventually we come up with a way of finding what we call the equivalent resistance. So this is commonly referred to as the equivalent. And what that means is that is the resistance that these two are acting as if they have. In other words, if we combine them together, if we replace them with one resistor, what would it appear to be? So let's take a look at an example. Let's say you have a 6 ohm resistor and a 3 ohm resistor that are connected in series. They're connected across a 12 volt battery. We're going to try to find a variety of things. We're going to assume the battery doesn't have any resistance itself. Batteries actually do, but for all of our sake, we'll kind of ignore that. We're going to try to find this current that's actually passing through the system, how much power each one is dissipating, and what the total power is. So the first step is we really need to figure out what this equivalent resistance is. But the nice thing is that's just the sum of these two resistors. So once we find that, the equivalent resistance is 9 ohms. In other words, these two act like a 9 ohm resistor. That makes it a lot easier because now when I'm looking at this little circuit and trying to find out what I is, I just have to worry about the 12 volts and the 9 ohms. So I can figure out the current by taking the total voltage over that equivalent resistance, or sometimes called the total resistance. And I find out I have 1.33 amps running through this thing. Well, since that's the same current going through each one, this one has 1.33 amps, and this one has 1.33 amps because there's only one path, so there's only one current. Then I can find the amount of power. I just have to find the right equation. I use the I squared R one because we've got current, we've got resistance, and we can find it. The reason I didn't use the one with V in it is because I didn't know the voltage of each one. They don't have the same voltage in this particular case. They're going to have different voltages. We could actually find that if we wanted to. We could use, we didn't ask this, but we could have used the V equals IR, and we could have done this for each one. We could have found the 1.33 amps times my 6 ohm resistor and found the voltage there, and then did the same thing with my 3 ohm resistor. We would have found this out. Since 1.33 is really 4/3 of an amp, and I multiply that by 6 ohms, this would have given me that the voltage across the first one was 8 volts. So this one is using 8 of my volts, and do the same thing, but replace this with a 3, and you'd find out this is using 4 volts. And the cool part is 4 plus 2 adds up to 12. I kind of think of voltage as being related to the amount of energy. So it's related to kind of how much energy it takes to go through each one of those. And whenever you have electricity go through, you always start out with the full voltage, but as you go through, we sometimes refer to these as voltage drops. In other words, they have to take away that voltage so that when you come back to the battery, this better come back as 0 volts. So the voltage difference or the potential across here is a total of 12. So 0 on one side, 12 on the other. Then they finish out with their power. I think we're pretty good. Next up, we have what is called parallel circuits. So parallel means they're connected in such a way that they have the same voltage across it. So if I notice here, I have a wire coming up to this resistor, or I have a wire coming up to this one. Commonly, we kind of draw this way so we can see that. So I have current coming out. This is a total current coming out. But when it reaches this little junction, some of it's going to go this way, that's I1, and some of it's going to go this way, that's I2. So we actually have the current splitting up in this particular case. So we have different currents, and we always find that we draw more current for the total. Good example of this is the outlets in your house, because we want to make sure they all have the same voltage. So if I plug in my TV or my stereo or my light bulb, they're all going to get that 120 volts. That's what we have at our house. Because the current splits up, we can think of the total current as just the sum of those. And then if I replace those with V over R, because that's how we find current, we can factor out the voltage because it's going to stay the same, and we come up with this little relationship. And what this is telling me is RP here would be the equivalent resistance for these resistors. And it's kind of a funny thing. We usually write it like this, that it's a ratio equals the sum of these reciprocals. The way I kind of think of it is a three-step process. When you're trying to find the equivalent resistance of things in parallel, take the reciprocal first, then you're going to add them together, and then you would take the reciprocal of that final answer. So if you notice, it's reciprocal, add, and then you have to take the reciprocal again, because you don't want 1 over RP, you want just RP. Let's take a look at an example. Let's say you have a couple of speakers, a 4 and an 8 ohm, connected to your receiver, and with this they have 6 volts connected across them. So the circuit looks like this. We're going to try to figure out the equivalent resistance and the total current and all that lovely stuff. The first thing I would do is realize that I have the 4 and the 8. I do it this way. I do reciprocals. So I would take 1/4 and 1/8. Then my second step is add. So I would add them together and figure out what that is. So that's going to be 2/8 plus 1/8. So this would add up to 3/8. The common thing is that's the final answer, what people think of. But the last step is we have to take the reciprocal of that. So my equivalent resistance here of these things in parallel would actually be 8/3 of an ohm. Check me out. 1/8 plus 1/4 is 3/8, and then I have to reciprocal to figure out that RP is 8/3, 2.6 repeating. Awesome. Then I can take that quantity and use it for everything else. The RMS here is just the fact that we're talking about alternating current. So the voltage is kind of alternating and the current is alternating. We're not going to worry about that as much. I just want to know it as a voltage or a current. So we take our 6 volts over that resistance, find the amount of current going, and then we can flip that over. Since the current is is splitting up, we can find how much current is going to go here, how much current is going to go there, because they have the same voltage. So notice this one is getting 6 volts, and the other one's getting 6 volts, and we find the currents. You should find that these two add together to give us our total, and sure enough, they do. And then we just work from there to figure out everything else. So that's a little bit on series and parallel circuits. The last little step is, what if we start getting combinations of those? For example, let's say that I had a complex circuit here. It's connected across 24 volts, but it had 110 ohm, 180, 220, and 250, and they're all connected like this. This is what we call an electrical diagram or a circuit diagram. What I use is I use little pieces of that and I bring them together. I find the equivalent resistance of those little pieces. For example, I notice that this 220 and this 250 are in series with each other. So when I combine them together, I just have to add them together. So 220 and 250 is 470. Then I look for another combo. The next combo I see is that the 180 and that 470 are in parallel with each other. So I would take 1 over 180 plus 1 over 470 and combine them together. I don't know what those equivalent pieces are, but I could probably do that on a calculator pretty easily. Eventually, what I find is that they together act like a 130 ohm resistor. Last but not least, this 130 and this 110 are combined together. They are in series with each other. Don't worry that they're on different sides of this. Think of it in terms of the current. If I have current coming out of here, it has to go through here and it has to go through here before it gets back. So that's what makes this in series. It's just like up here when I have to go through here, but then I have this little junction where I can split. Some of it goes this way and some of it goes this way. And then over here, the reason these were in series is there was only one path. They had to go through both. So when I combine those two that are in series, I get 240 ohms connected across a 24 volt. And then the cool part is then I can go from there and I can work my way backwards through my pictures to figure out, like, maybe I want to know how much total current comes out of this thing. So the total current would be my total voltage over my total resistance. So 24 over 240, that would be 1/10 of an amp. And then I can work from there and figure out, okay, that means each one of these gets 1/10 of an amp. And then I kind of work my way back and figure out that they're going to split. How much did they split? They should get the same voltage that this resistor got. So we can kind of go from there. So kind of neat. We'll play around more with that next week. Just wanted to start you off. Hope you enjoyed. Talk to you later.